Okay, so here's where we're picking up from last time. So last time we talked about this business about right-hand order, right? And it's kind of a three-dimensional version, sort of a three-dimensional modification of the ideas of clockwise and counterclockwise, which are super intuitive in two dimensions, right? I mean, something we've got great personal familiarity with. So right-hand order is, not so really such a different concept. Okay. What does that connect to, you ask? Well, it, among other things, connects to the idea of determinant. So, some of y'all, probably most of y'all have seen determinant at some point in the past. There's a lot to say about determinant. We won't come anywhere close to saying all of it. Just going to show you couple of interesting facts about determinant that connect to what we're doing right now. So here's the definition of a 2x2 determinant. It's an easy little formula, AB minus BC. So when you're looking at a 2x2 matrix, you multiply the diagonals, and then you multiply the off diagonals and subtract, which seems weird, right? So why the minus sign? Don't look for intuition there. It's very hard to get that intuition. We won't be able to do that in this course. Here's a formula for a 3x3 determinant. Now, notice we're using a different formula for determinant here. We're using this notation here. It looks kind of like absolute values, which is, let's call it unfortunate. But anyway, common notation. So what this says, if you want to take a 3x3 determinant, you do so by the following combination of these 2x2 determinants. And the way you can kind of think about this is that we're going along the top row. Note A1, A2, A3. For each position that we're in on the top row, for example, let's look at the A2. You cross out the row that it's in, you cross out the column that it's in, you look at the remaining four elements, right, and you make a matrix out of them. Right, so that's the sub-matrix associated with that position on the top row. And then don't forget, there's one other little detail. Note that there's a minus sign there. And again, why the minus sign? It seems out of place. It's a plus here, it's a plus there. Why the minus there? Again, don't look for that intuition. In this course, we're not going to be able to talk about it really at all. So anyway, but you do need to know the formula for how to compute a 3x3 determinant, and of course also for a 2x2 determinant. Okay, it seems like an arbitrary formula. Again, seems like it's far too simple to possibly be meaningful in any interesting way, and yet it does some pretty remarkable things for us. Here's the first thing that it does. There's a big theorem. It takes quite a bit of space to state this theorem. Let me tell you what this theorem is really doing, though. Suppose we have a couple of vectors in R2. Notice this is in R2. So this is the two-dimensional version of the theorem. And let's suppose our vectors are that and that, A and B. All right, so A and B. And I'm going to notice that there's a couple of things that I can generate from those two vectors. On the one hand, I can make a matrix out of those two vectors. So I could take the first vector listed, that's the A vector, make that the first row of a 2x2 matrix. Then I can take the coordinates of the second vector listed and make that the second row. And lo and behold, I have a matrix. Okay. Now, here's another thing that I can generate with that pair of vectors. I can generate the corresponding parallelogram in R2. All right, so given a couple of vectors in R2, you can make a matrix out of them, you can make a parallelogram out of them. And the amazing thing is that the matrix and the parallelogram are related very strongly by way of the determinant. So, in particular, the determinant of this matrix tells you two things. On the one hand, it tells you whether this listing is in clockwise or counterclockwise order. So note whether the vectors are listed counterclockwise or clockwise or neither corresponds perfectly with whether the determinant is positive, negative, or 0. It's really surprising, right? Wouldn't you think that the process of deciding about which way do you rotate, I mean, my gosh, it involves angles. Shouldn't it have an arc cosine in it somewhere? Nope. AD minus BC, real simple little formula, right? We'll decide on whether it's clockwise or counterclockwise. It's amazing. The other thing that this theorem tells us is about the area of the parallelogram. Turns out that the area, in all cases, whether the determinant is positive, negative, or 0, the area is always the absolute value of the determinant. So the determinant then answers both of the questions, both geometric questions you might be interested in about this listing of vectors here. The determinant sign tells you whether it's clockwise or counterclockwise as a list. The determinant's absolute value tells you about the area that they make. Again, really surprising. I mean, area. Well, don't you have to drop a perpendicular? Shouldn't there be a sine theta involved somewhere or something? Shouldn't it depend on how long this vector is? Doesn't it have a square root in it? How is three-function arithmetic answering this question for us? It's very counterintuitive, but nevertheless true. I'm not going to prove this theorem in Math 212. My favorite way to prove this theorem involves using some methods that are a little bit too sophisticated for this class. And rather than prove it a way that I don't prefer, I'm just going to skip the proof entirely. Okay, which, by the way, is not a big deal. And, of course, like Math 212, it's very reasonable. Okay, there's a three-dimensional version of this theorem. So instead of 2 vectors in R2, what if you have 3 vectors in R3? And something highly analogous works. So if you have a list of 3 vectors, you can make a matrix out of them in the same way. Take the vectors as listed, make them the rows of a matrix. Okay. First one is the top row, second one second row, third one third row, just like you would think. Likewise, take those 3 vectors, make the corresponding, kind of box-shaped thing that we have here. Now I got on the wrong side. There we go. Make this corresponding box. We call this a parallelepiped. And the determinant answers 2 very natural questions. Whether the vectors listed are in right-hand order, left-hand order, or neither order, and thus keep in mind, neither means it's not right, it's not left, it's, they're all coplanar, they're all parallel to the same plane. Maybe 2 of them are parallel to each other, maybe one of them is a 0 vector, something makes them all parallel to the same plane. Right hand, left hand, or neither is entirely decided by whether the determinant's positive, negative, or 0. And as you would sort of expect, in all cases, the determinant, by way of its absolute value, gives you the volume of the parallelepiped. So again, both aspects of the determinant are interesting. The sign tells you about the handedness. The magnitude tells you about the volume. So in both cases, we have really surprising connections between this algebraically defined determinant and these really intrinsically geometrically natural ideas. Handedness. That's really geometric, right? Volume. You can't get more geometric than that, right? And yet they're both connected to this formula that we defined in a really algebraic and really arbitrarily algebraic way. Okay. All right. Quick example then. Here's a trio of vectors, and it'd be a pretty hard drawing, graphing, interpreting problem to actually make these vectors 3-dimensionally and then look at them and try to decide, is it like that, or is it which side is it on that side or that? It'd be really hard to look at this and just decide with a pencil and a piece of paper. is that right-hand order or left-hand order, and certainly it'd be a hard problem to compute the volume. But taking these three vectors, 1, 2, 3, 1, 2, 3 to make a matrix. Take the determinant, usual formula, you get negative 10. That tells you two things. The minus sign tells you that this list in that order is a left-hand order, right? And the magnitude, namely 10, tells you the volume is 10. The volume of the parallelepiped defined by those vectors. So, super convenient computation. Okay, so we've talked about right-hand order and left-hand order as a concept. We've talked about determinant as a computational tool related to that. Now I'm going to introduce a third idea that's actually connected to both of them, and that is the cross product. Here's the definition of the cross product of two vectors. Here's the formula. You just have to, I'm just going to assert that this is geometrically natural. Right now I've given you no justification for it, but I'm going to persuade you, I hope, over the next, I don't know, hopefully not too terribly long, 20 minutes I'm hoping, that this is supernatural geometrically. I don't mean supernatural, I mean it's extremely natural geometrically. Couple of observations I want to make about this formula. It's very different from the dot product in a qualitative way. The cross product of two vectors is another vector. Shouldn't it be? Wasn't it seem weird that the dot product of two vectors was not a vector, it was a scalar? That was weird. This is back to normal in some sense. So the cross product of two vectors is another vector. Another big difference, the dot product, we only wrote down the formula for the dot product in R3, and then I think I made some statement about it. There's an analogous formula in R2, it's exactly what you think it is. Side note, there's also an analogous dot product in Rn. This is exactly the same process. You take the coordinates of the corresponding vector, you multiply them pairwise, and add up the products. It's exactly the same process. So dot product generalizes in lots of different dimensions. Cross product doesn't. Cross product is a peculiarity of 3 dimensions. There is no cross product in R2. There isn't really a cross product in R4 or higher. There's a kind of a, it's not a binary product. There is an operation that serves, that plays a role kind of analogous, but as far as we're concerned, there is no cross product in anything other than R3. So you got to keep that in mind. Okay, this formula, I'm actually going to recommend that you don't memorize it, because there's a more convenient memory tool coming up fairly soon. Right? So good news, you don't have to memorize that formula. Yeah.
We won't use cross products in R2.
It doesn't exist in R2, and it, as far as we're concerned, no such product exists in R4 or higher either. Okay. Yeah, it's a peculiarity of R3. Right. So as I've done before, I'm going to start off with some properties. Whenever we define a new operation, we write down some properties, and they're mostly yawns. A times B is equal to B times A. Well, of course it is. Dot product of V and W is equal to the dot product of W and V. Oh, boring, right? Look at this. Cross product. These are all true properties. And they don't look like you would sort of expect a product to behave. Check this out. The cross product is not commutative, right? There is a minus sign there. That's weird. Heads up, right? If you're doing algebra cross products, don't just treat this like algebra of, high school algebra. I'll just kind of whip things around in ways that are different. No, that minus sign, that's a big deal. This next one's really weird. This is a property that involves cross products and dot products. And if you, it's strange. If you take a cross product of V and W and then dot it with U, you wouldn't think there'd be any connection to what happens if you take crosses of U and V. Well, I wasn't even crossing U and V over here. But if you cross U and V instead of V and W. And then dot with W. Note W was not part of the dot product over here. It seems like these should be unrelated. They're equal. Weird. Likewise for the next one. I will draw your attention to one thing here, by the way. Notice that I only listed 3 things that are equal to each other. I didn't list all 6. There's 6 different ways that you can arrange 3 things, right? But only these 3 are equal to each other. Notice that U dot W cross V is not equal. Well, of course it's not. W cross V is the negative of V cross W. So these 3 things are equal to each other. The other 3 that you could write down are all equal to each other, just not these. Right? They're negatives because of the first property. Okay, last one. If the cross product is the 0 vector, then it means either the vectors are parallel or one of the vectors is the 0 vector. In general, it means that one of the vectors is a scalar multiple of the other vector. Okay. All right. So now we're gonna see why these are true, all of them. You can just kind of write down algebraically and prove all of these. In fact, it's a homework exercise to prove the third one. But we're going to come up with some geometric interpretations that make all of these geometrically satisfying in addition to algebra that you can crank out and check. It's going to take us a bit to get to it. Important theorem, one of the most important things we'll do with the cross product. Right here. If you take any 2 vectors V and W, if you cross them to make V cross W, the product is always orthogonal to both of the input vectors. It's weird. You take any 2 vectors, like, I don't know, that vector and this vector, the cross product of those 2 vectors is going to be perpendicular to both of them. I don't know which way, we'll talk about that in a minute, but it's going to be, well, I should say orthogonal to both of them. Now, I have to say orthogonal. I can't say perpendicular. If I said perpendicular, that would suggest that the cross product wasn't the 0 vector. Of course, the cross product can be the 0 vector. That's kind of annoying. But here's why it's really convenient to have this word orthogonal. It is always orthogonal. It's one word that encapsulates all the possibilities of how the cross product might behave. It might be perpendicular, it might be 0, but either way, it's orthogonal. Okay, so to prove this result, there's a couple of computations that you have to do. This, right, if you compute this and confirm that you get 0, let's think about what the result would be. V cross W, well, if that's 0, then I have a dot product equaling 0. Now wait a second, rewind to yesterday. If a dot product is equal to 0, that means that the 2 vectors in question are orthogonal. Right? So this calculation here would confirm that the cross product is orthogonal to the V vector. We've proved half of the theorem. The other half of the theorem comes from computing this dot product. Excuse me. Take this dot product. If you get 0, it means that V cross W is orthogonal to the W vector. And we're done. It's just algebra. This is a good exercise for everyone to do. We have formulas for we have formulas for cross product. We have a formula for dot product. So this is just brute force, plug and chug. So I encourage you to compute both of these things. It's not that bad even. It's just 6 terms in each calculation, and it just turns out they cancel. Okay. All right. So here's a different formula for the cross product. Different way you can think about the cross product. Let me use a different color other than yellow. Let me use green. Different formula for the cross product there. Note I'm expressing the cross product as a linear combination of E1, E2, and E3. So this is just kind of an alternative way of saying that the components of V cross W, the coordinates of V cross W, are these 3 determinants. Oh, hey, whoa, slow down. Note that minus sign. But the coordinates of this cross product are these 3 determinants with the minus sign in there. And that's just an observation. Just notice that, yeah, sure enough, that is a 2 by 2 determinant. Looks just like an AD minus BC. That is the determinant of a particular little matrix. Ditto this and ditto that. Do be careful with the minus sign, of course, on the second one. Okay, so you guys can do that for yourselves. Confirm that the cross product is that combination involving 2x2 determinants. Now, having noticed that, now look at this whole formula by itself, and notice that that whole formula kind of looks like a 3x3 determinant, doesn't it? Right? I mean, the structure of this looks like a 3x3 determinant. It's 2x2 determinants, plus, minus, plus, and then multiplied by these things, E1, E2, E3. It's as if we were taking a 3x3 determinant of this matrix, and I'm going to do the air quotes when I say matrix here. A matrix is supposed to have entries that are numbers, right? These aren't numbers. E1 is a standard basis vector, not a number, and likewise E2, E3. So this is not really, I mean, I don't know. It's a weird, we're not clear we should be calling this a matrix, and it's not clear what we would mean by the determinant. Certainly I can't visualize this determinant as being representing a parallelepiped. Yeah, not really. It's just not a vector up there, right? But if you just kind of forget about that, right, and take what we consider a symbolic determinant of this symbolic matrix, I mean, as symbols on a page, it looks like a matrix. Just ignore that it doesn't make sense. If you compute this determinant, sure enough, you get exactly that. Okay, so this is the formula I want you to memorize. It's really easy to remember. If you want to take a cross product, just put the standard basis vectors across the top. The next row, put the coordinates of the first vector. The last row, put the coordinates of the second vector. Take the formula, apply the formula for determinant in the usual way, and it will compute your cross product for you. It's a much easier thing to remember than that. Right? For the life of me, try as I have, as I have on several occasions in the past, I can never remember if the second one is it V3W1 minus V1W3, or is it V1W3 minus V3W1? It's just so hard to remember. So rather than take the risk that you'll remember it backwards, just memorize that. You're good. Everybody happy? Okay, now, next observation I want to make. If I were to take this expression here, U dot V cross W. Now let's think about how would you compute a dot product of U and V cross W? Well, U has coordinates U1, U2, U3. V cross W has coordinates, here they are. V cross W has coordinates that determinant, don't forget the minus sign, and that determinant. Note that's all I have written down here. 1, 2, 3. And see what I have then is I'm computing this dot product. That dot product, green dot blue, I'm computing as, well, multiply the coordinates and add. That's a straight up, just plug in, and sure enough, you see that that's that. Then you notice again, that looks exactly like a 3x3 determinant, like that. So what we have then is a really surprising formula about the cross product. The cross product with a dot product gives you a determinant. This ends up being a really big deal, by the way. So another really important formula to memorize. So yeah, very important to memorize that one in order to compute cross products. This one's very important for reasons that we're going to see in the next couple examples. By the way, this is called a triple product sometimes. A dot product with a cross product called a triple product. And the fact that that triple product is a determinant is a really big deal. And a rough, why this is so important is because we already know good geometric interpretations of the determinant. we already know good geometric interpretations of the dot product. And that's going to help us make geometric interpretations about the cross product. Right? If you have an equation that relates stuff you don't understand with stuff that you do understand, right, that's promising. Okay, so here we go. First little bit of intuition I'm going to give you is, why is it that the cross product of two vectors is always orthogonal? Now, we already proved that. Well, correction, I left as an exercise for you guys, and you're going to do it on your own. But you're going to compute these two dot products to show that the V cross W is orthogonal to both P and W. And at the time, we were thinking of these as dot products, which is fine. But now let's take another close look at these expressions and notice, yeah, they're dot products, but they're also triple products. So rather than brute force this, let's compute these triple products. Let's look at this one here, V dot V cross W. Let's look at that triple product and try to interpret it a different way. Here we go. That triple product is this determinant, per the formula on the previous page. Determinants are volumes. So what I'm trying to compute, in fact, is the volume of the parallelepiped that I get by looking at the vectors V and W. And here's what that parallelepiped looks like. There's the V vector. That's the first vector. The second vector, also the V vector. Right? And the third vector is W. So this dot product, this triple product, this determinant, we're looking at a volume of a parallelepiped defined by three vectors, but two of the vectors are the same vector. Now just use your geometric imagination. What happens if you think about the corresponding parallelepiped? What happens if two of these vectors close in on each other like that? And I appeal to your geometric intuition. The box turns flat. Right? This is the kind of parallelepiped that you would get. It's like, I don't know, y'all may not have to recycle boxes when you order something from Amazon. I have to recycle a lot of boxes because we order stuff on Amazon, right? And you take a box and you get rid of the bottom and the top, and it's got three edges. Once you start to fold it, right, the two vectors defining these two edges, as those two edges approach each other, the box just folds flat. It looks just like this. What can I tell you about this box? Well, the volume. I mean, this is prepared for recycling. The volume is 0. That means the determinant is 0. That means the triple product is 0. That means this dot product is 0. That means that V and V cross W are orthogonal. Isn't that neat? Right? I didn't have to actually calculate anything. I just observed, well, orthogonality relates to a dot product, which relates to a triple product, and a determinant, and a volume, which is easily understood, and then back you go, you get the result you want. Really neat argument. Okay, here's the next cool argument that we're going to make. This theorem, different ways to prove it. I like this one best. If you take the cross product of V and W and look at its magnitude, any two vectors V and W, the magnitude of that cross product tells you the area of the parallelogram that those two vectors define. All right, so it's very surprising. You take two vectors, just two, right? You want to talk about the cross product of those two vectors. We already know it's perpendicular to both of the two vectors. The length of the cross product tells you the area of that parallelogram. Very surprising result. Okay, I'm going to prove this theorem for you with another. Recall the term that I introduced last time, the mathematical bank shot. Right? I'm going to prove that these two things are equal to each other by starting off thinking about neither one of them. I'm going to start off by thinking about something I ultimately don't really want to know about. All right, so I'm going to head off in a direction we don't seem to be interested in. I'm going to think about that. And you'll see why in a moment. But it turns out that this determinant, where the rows are the cross product, then V, then W, this determinant relates to the magnitude of the cross product, we're going to see momentarily, and it relates to the area of the parallelogram, and that's going to allow us to draw our conclusion. So very weird little idea. So here we go. First observation about this. Now keep in mind that very specific determinant. That determinant is a triple product. Now let's be careful as we write this down. The first vector dot second vector cross third vector. Right? So all this says is this first equation I've written down is that triple product. Excuse me, a determinant is a triple product. And you can start to see the clever move that I pulled here by choosing which vectors went where. I've arranged for this triple product, you now notice, to be a dot product of a vector with itself, and we know that that is magnitude squared. All right, everybody good? We're not done. We haven't proved anything yet. We certainly haven't proved anything about area. But I've connected the bank shot object with magnitude, which is one of the things I care about. Okay, next part of the proof. I know that determinants give me volumes. Right? Oh, by the way, how do I know that the determinant didn't give me the negative of the volume? Yeah.
Isn't our cross product squared, so we know it's going to be positive?
That's exactly right. So it's exactly what I was looking for. We don't have to worry about the absolute value of the determinant because we can see right here that this thing, is clearly a square. So it can't be negative. Right? So this gives me volume. Right. Okay. Now what is the volume of this parallelepiped? Now again, we have three vectors: cross, V, and W. And here's what that parallelepiped looks like. Here's the V and the W. We know that the cross product is perpendicular to both of them. So I want to compute this volume. And now I'm just going to remind you of an old geometry formula from long, long ago. The old geometry formula says that because of the perpendicularity, the volume is that distance times this area. Right? Y'all remember the formula for volume of a cylinder from high school geometry? So volume is equal to area of the base times the height. I mean, this is at some angle, but who cares? They're perpendicular. That's the point. So okay, area, which is the area of the parallelogram that I'm interested in. And the height is the length of the cross product. So down here, determinant is volume. And the volume, as we just discussed, is colors. What color did I use? Green for the area and purple. Magnitude of the cross product is the height. Okay, so what have I done? Keep in mind this is a mathematical bank shot. I don't really care about this object here. I'm not clear why I'm interested in that, but I have shown that it's equal to that, and I've also shown that it's equal to that. Now, I don't really care about this thing, but since it's equal to both of these things, that means that these things are equal to each other, and I care about both of these things. And so notice you just cancel common factor of magnitude here, magnitude of V cross W, and you have that magnitude equals area. So it's a really clever argument there. I think it's lovely. Gives us the desired result. Magnitude of the cross product is the area. Okay. This corollary here is just a variation of that. I'm going to let you all take a read on this. All this corollary is, note it's still telling you how magnitude is equal to area, but it just gives you an alternative version of it, and that just comes from trig. looking at this triangle sitting inside of that parallelogram. So y'all can read that on your own. Okay, so we have a pretty good characterization of the cross product at this point. Recall that, given two vectors, I know that the cross product has got a point perpendicular to both of the input vectors. Now, given a v and a w like this, keep in mind there's two different directions, right? That are both, this and that are both perpendicular to both of those vectors. I just don't know which one. So, but I do know the area, right? The area of this parallelogram. That tells me the magnitude. And so the cross product that I'm looking for is either that vector or that vector. I just don't know which of those purple vectors it is yet. I know it's either this direction or that direction, and I know exactly how long, so that cuts it down to two possible vectors. Which one is it? And this resolves very nicely. We go back up to what we just argued and recall this calculation that someone's already observed here very nicely, that this determinant is positive. That means that this listing here, cross, V, and W, that listing, because this is positive, that tells you this listing is a right-hand order. All right. So let's come down here. Let's see, where do I write that down? Yeah. So that is a right-hand order. And recall from the discussion of right-hand order, you all remember this business. You can sort of cycle the vectors in a right-hand ordered listing. It remains right-hand ordered. That means that this is a right-hand order. So this is what we end up making the most use of. The fact that V, W, cross product is always a right-hand order. So people call this the right-hand rule. If you're taking a cross product of two vectors, first vector, index finger, second vector, middle finger, again, rotate your hand as needed. Your thumb will tell you which way the cross product goes, because V, W, cross product is always a right-hand order. Okay. So it turns out that this gives you a completely geometric characterization of the cross product. Some books, in fact, even define the cross product like this. That the cross product of two vectors, V and W, is the unique vector that's orthogonal to both with magnitude equal to the area of the parallelogram and that satisfies the right-hand rule. That there's always exactly one vector that satisfies these three properties. You can make that the definition of the cross product. It's just kind of hard to work with, so I think it's a weird definition. I like the formula, right? But anyway, it's equivalent. So what's nice about this, though, is that we started off this discussion by saying here's a random formula for cross products. Weird algebra, just compute this, right? With no geometric intuition, and now we see that everything about it is actually geometrically natural. Okay, all right, so that's all I have time to discuss. There's an example here y'all can read if you'd like. That's all I have time to discuss on cross products and determinants. It's a fun section. Lines and planes. This is a pretty quick section, by the way. I'm going to do this reasonably quick. I'm going to start off by deriving the equation of a line in R2. Now, I know y'all know this already. Y equals mx plus k. Ancient history, right? And you also know this one. Let's see, where'd it go? Ax plus by equals c. I never liked that one when I was in school. I always liked this formula because it's so communicative. Right? M means something. It's slope. Right? K means something. I can interpret what, knowing what K is, that tells me geometrically what's the y-intercept, right? It's really handy and useful. Whereas this ax plus by equals c thing is just always, I don't know, I guess it's organized or something. You got all your variables on the left and your constants on the right. But it just seemed kind of like, what do you get from that? What does A mean? Right? No one ever told me any interpretation for what A is. Okay. All right. Anyway, I'm going to show you a different point of view on lines. suppose we're told that we're interested in a line and we're given a point x naught that the line goes through, and we're also given what I'm going to call a normal vector in. Just FYI, the word normal the word normal means lots of different things in lots of different contexts. In this context, normal means perpendicular. That's kind of weird, but anyway, notice this is a vector that's perpendicular to the line in question. Now, I claim that if I'm told this information, if I'm told, well, the line goes through this point and is perpendicular to that vector, that characterizes the line, right? There's only one line that could possibly be perpendicular to that vector and goes to that point. Okay. So from that, let's derive the equation of this line. There's a nice argument for how to do this. It starts with a test. Let's talk about how would I test if that point is or is not on the line L. And the first observation I'm going to make is that, well, I mean, we're given that x naught is on the line. So if x is also on the line, then that difference should be parallel to the line. Whereas if it's not on the line, then that difference would not be parallel to the line. Right? So whether or not x minus x naught is or is not parallel to the line entirely determines whether or not the point x is or is not on the line. Okay. Everybody happy with that? I'm going to start off with that down here. So the point is on the line if and only if x minus x naught is parallel to the line. Now recall n is perpendicular to the line, so parallel to the line means perpendicular to n. Zoom in one notch here. So parallel to the line means perpendicular to n. Perpendicular to n means dot product is equal to 0. Right, so this is a slick move. Notice that we started off talking about some geometric statement, and I've changed the statement to a statement about parallelness, and then to a statement about perpendicularity, and that allows me to rewrite as a statement about dot products, which is algebra. Right, so I've successfully changed a geometry statement into an algebra statement. This is a very important trick. Right, being able to, if you're given statements about geometry, that's how problems come to you. Hey, I need this to be perpendicular to that, or I need that thing to have the geometric feature that blah, blah, blah. How am I going to do that? Very often, step one is translate the question somehow or another into a statement about algebra. We love algebra because we can do algebra. We've got algebraic properties and rules, and we can get our hands on it. Right? So being able to translate into the language of algebra is a really big deal. And that's what I've done here. And now notice this is just a rewrite. You can distribute the dot product. Take this term, move it over to the other side of the equation, and lo and behold, there's the equation for the line. Now it's not familiar looking, but if you just, let's see, where did I do this? Yeah, here we go. If you just choose to give names to the coordinates of the normal vector, let's just call it a comma b, right? And the point you're testing, x comma y, then n dot x is ax plus by. N dot x naught, well, both of those vectors were given, so I guess I could write down names. I could call this vector, I could say it has coordinates x naught and y naught, and I could write that out. But the point is, it's all given, so this is equal to some number. Let's just call it c. And there's the standard form equation for a line in R2. And nobody told me this when I was in, I don't know, when do you first learn about equations of lines? Is that Algebra 1? That's probably Algebra 1, right? Very frustrating when I first saw this argument. I thought, oh, that's why this is a natural way to write the equation of a line. A and B do mean something. A and B tell you the coordinates of a vector perpendicular to the line. That's a kind of handy. It's a big deal. A and B are your normal vector. Sweet. Okay. All right, so this is, you could say that's, we're just cleaning up a little bit of a mess from high school algebra, but there's a more important application, and that is that you can use the same argument to come up with the equation of a plane. So here it goes. Suppose you have a plane that is known to be, it contains that point x naught, and it is perpendicular to that vector n. So again, I appeal to your geometric intuition. There's only one plane perpendicular to n. Well, there's lots of planes perpendicular to n, but there's only one of those planes perpendicular to n that actually goes through x naught. Right? So these two bits of information, n and x naught, characterize a plane. I can test any point x as to whether it is or is not on the plane by looking at whether that difference vector is either parallel to the plane or not parallel to the plane. Just like in the line case, right? Which, by the way, means either perpendicular to the normal vector or not perpendicular to the normal vector. And you see the argument goes through exactly the same way. Parallel to P, synonymous with perpendicular to the normal vector. Perpendicular means dot product equals 0. Distribute the dot, move this over to the other side. It's the exact same argument, and you end up with n dot x equals n dot x naught. The only difference here is that now your normal vector, I better zoom in for emphasis here. Now your normal vector, n, has 3 coordinates, a, b, c. Right? The point that you're testing, x, has 3 coordinates, x, y, z, and so the dot product now has 3 terms. So you get ax plus by plus cz equals d, but I mean structurally it's not that different from the equation for a line. Isn't that cool? Again, make sure to remember what this means is that when you see the equation, when you see an equation in this form for a plane, the form is telling you something, right? A, B, C. Those are not just meaningless random numbers that just kind of coincidentally happen to work out that way. A, B, C, those as a trio tell you the coordinates of a vector n that is perpendicular to your plane. So geometrically very important information. Okay. Alrighty. So quick example, super quick. There's a unique plane that contains the point 152 and that is perpendicular to the vector -2, 1, -4. And it's just so easy to write it down. Perpendicular to that vector means that's my n. Right? Passes through the point 152 means that's my x naught. And then you just plug in. N dot x equals n dot x naught. And there's the equation of your plane. Cool. Along those same lines, no pun intended. Suppose you have a plane and what you know is that it passes through these 3 points here. So the awkwardness is that we're not given a normal vector. Right? If I'm going to write down the equation of the plane, I need the normal vector. I don't have a normal vector. I do have an abundance of possible x naughts. Right? X naught could be any point in the plane. I have 3 of them. We're good on x naughts. Right? So take your pick. It doesn't really matter. But we still have to figure out how to compute n. And this begins a kind of a standard sort of geometry puzzle. Here's my situation. I have A, B, and C that are all in the plane. And you need to find a vector perpendicular to the plane, and think about what you know, what kind of tools do you have at your disposal, and what can you conclude about, when you apply a certain algebraic operation, what can you conclude geometrically? So for one thing, because A and B are in the plane, B minus A is parallel to the plane. Right? Likewise for C minus A. parallel to the plane. Now if I take these two vectors that are parallel to the plane, if I were to take their cross product, the cross product, by being perpendicular to each of them is parallel to this plane. Well, if this is perpendicular to both of the vectors parallel to the plane, then that means this cross product's got to be perpendicular to the plane, and that's what we wanted. Right, so, notice there's kind of a three-step process here, and in these 3 steps, there were certain algebraic moves that I pulled, to which I have associated geometric interpretations. That allows me to sort of keep track geometrically of what have I got as I go along that process.
So basically, since you don't have the normal vector, you just, by knowing the cross product is going to be orthogonal and perpendicular, you just substitute that.
Yep. I just use that as a normal vector. By the way, that reminds me one thing I wanted to mention. So when you have a normal vector, here let me just let me use a different picture. Let's come back up to here. So let's suppose that this normal vector has coordinates a, b, c. You might wonder, hey, what about that vector? 2a, 2b, 2c. Can I use that? I mean, why isn't that the normal vector? Is it just as good, but what's with the 2's, and how does it? Is that okay? Can you just multiply by 2 like that? And it turns out, yeah, sure you can, because check this out. Your equation n dot x equals n dot x naught, right? That equation tests for whether x is or is not on the plane. Now let me take this equation and multiply by 2 on both sides. That's perfectly legal. And now let me just put some parentheses like that. And notice that that 2n also could just as well serve as a normal vector. So you can scale normal vectors however you want. You do have to pick one and stick with it, right? But what the magnitude of that normal vector is kind of arbitrary. It doesn't really matter. Okay. What about lines in R3? We've talked about lines in R2. We've talked about planes in R3. But lines in R3, different story. There's a temptation to say, well, let's try to find the equation for a line in R3. If you think about it, it doesn't make sense. If you take an equation in R3, that's going to give you a plane. We just did that. Right? So there can't be just an equation, really. Certainly not a linear equation. So there's a different sort of geometric sort of perspective to take here, and that is, here's a line in R3, you notice? And I assert that that is characterized by a point on the line and a vector parallel to the line. You give me a v vector and an x naught point, that defines L. Right? And, I mean, we can do a similar process. We can decide on whether a vector x is or is not on the line by whether or not the difference vector is or is not parallel to the line, or is not parallel to v. Right? So you write that down algebraically. Here it is. We decide on whether a point is on the line by whether x minus x naught is parallel to the line, aka parallel to the direction vector v. And let's think about this. What does it mean to be parallel to a vector v? Well, that would mean that this vector would need to be a scalar multiple of v for some scalar. And then just taking the x naught and moving it over to the other side of the equation gives you this. So we can decide whether x is on the line by whether or not it is possible to represent x as x naught plus tv for some yet to be determined value of t. Now, that's not a very handy equation if you think, if you give me an x and ask me, can you find such a t? Well, that's kind of weird. We'll talk about that in a minute. But there's a different point of view to take on how this is actually a pretty big success. Instead of thinking of this as a way to test whether or not a point x is on the line, let me just notice that I can plug in any value of t that I want. Doesn't matter. Any value of t, plug it in there, and this expression, x naught plus tv, will give me a point on the line. So this is not a point tester. This is a point generator. Right? You give me any value of t, out comes a point on the line. Right? You can plug in as many values of t as you want. Every time you do, out comes a point on the line. You're generating points on the line. It's a little factory for points on the line. So we call this a parameterization. We'll talk more about parameterizations a little bit later on. Very useful to be seen, details to come later. Here's an example. Suppose I want to find a parameterization of a certain line, and suppose I'm not given a direction vector. I'm given 2 points, A and B, that are on the line. And you just observe that if you know 2 points on the line, then their difference is parallel to the line, and you can just declare that to be your V. Oh, cool. Okay, this is a cool example here, 155. We're short on time, so I'm going to let you all read that one on your own, but definitely give it a look, 155. I want to talk about symmetric equations, and this gets back to what we were talking about a minute ago. You look at this equation here, thinking of this as a way to decide, you give me some point x, can I find some value of t that when I plug it in, the point that gets generated is exactly the point x that I was curious about? And it's a hard problem at a glance. Do I just have to start plugging in t's and keep my fingers crossed and hope that it works out? Or is there a more clever approach? So let me show you the more clever approach. And that is, let's look at these equations. And notice that this is just what we had before, x equals x naught plus t times, this vector a comma b comma c, which is our v vector. Okay, so looking at these equations, is there a value t that will generate a given x, y, z? So you give me an x, y, z. Is there a value of t that will generate these exact 3 coordinates? Now, very importantly, I need to know that there is a single value of t. One value of t that I plug in, and that one value of t gives me all 3 of these coordinates. Same value of t. Well, I can tell you what that value of t has to be. That value of t has to be that. Right? I mean, forget about the y and the z. Just looking at this first equation, if you've given me an x and you want to know what t is going to make these 3 points, well, it's going to have to give me that x. So the value of t in question has to be what this first equation says it has to be. It's got to be that. Right? Okay, but it also has to be what the second equation says it has to be. Likewise, t had better be what the third equation requires it to be. T is going to have to equal to all 3 of these things. Now let's ask the same question again, with that observation having been made. Is there a single value of t that can equal to all 3 of these numbers? Well, that's going to be possible if and only if these 3 numbers are all equal to each other. Right? If these 2 numbers are different, then no, there is no single number that can be equal to 2 different numbers. Right? It won't make sense. So the value of t will exist if and only if these 3 things are equal to each other. So this is a test. You give me an x, y, z. Well, put the x there and the y there and the z there, and if all of these equations, if these 2 things are equal and those 2 things are equal, then yes, I can call this shared value t, and that's the value of t that makes x, y, z true. Okay, so this, again, serves kind of like an equation now. You plug in the x, y, z, see if it works, see if it doesn't work. If it works, yes. If it doesn't work, no. They call this the symmetric equations of the line. Let me skip down to this next discussion. You take a look at this example again. It's a pretty straightforward example, but here's a different way to write those symmetric equations. If you say you need three things to equal to each other, then, well, I need the first one to equal to the second one. I also need the first one to equal to the third one. And I also need the second one to equal to the third one. So it's kind of three equations in a way. I mean, it's two equations, but it's kind of three equations, depending on how you look at it. So I want to look at these three equations and ask, well, what do these equations individually represent? And it turns out it's really interesting how this plays out. Let's think about this one here. What is that thing? Well, I'm going to make a couple of observations about it. First of all, that thing is a plane. I mean, it's not in the form that we normally write planes, but if I were to, cross multiply and move things around, I would have something times x plus something times y plus, well, there aren't any z's. Whatever, 0 times z, there'd be an x, a y, and this trivial z term equals some constant. Right? So this is a plane, however weirdly we've written it. Second thing, this contains the line. Now, how do I know that? What I mean by this plane contains the line is if you give me any point on the line, I claim that that must be on this plane. Now, let me say that algebraically. If you give me any point that satisfies all three of these equations, it also satisfies that one equation. It seems trivial when you say it like that. Right? If it satisfies all three equations, well, of course it satisfies this one. This is one of the three. Okay? So therefore, if it's on the line, it's also on the plane. Therefore, the plane contains the line. Okay, last thing, third observation. If you were to write down the normal vector for this plane, the normal vector is, there's some number, comma, 0. Right? Again, when you're collecting terms, moving terms around, there's no z's. So the coefficient of the z term is 0. That means that your normal vector is horizontal. Not up, not down, right? The normal vector's got to be horizontal. Now let's think about that. If the normal vector is horizontal, that means that the plane has to be vertical. This is a vertical plane containing our line. Said differently, that is the vertical shadow, I like to call it, of the line. So we started off with this line here. Get better than that. Started off with that line. There is exactly one plane that is, straight up and down vertical that contains that line. You can see why I call it the shadow, right? If you imagine sun straight overhead, this is the way the shadow would cast. So that's a pretty neat observation. The symmetric equations, if you look at the symmetric equations individually, they're the equations of shadow planes. So I've given you the argument for why the shadow plane, the vertical shadow plane is what it is. And I'm going to leave as an exercise for y'all. It's a great little exercise to see if you're really following along all these ideas. Try to persuade yourself that this one, right, the equation involving x's and z's, that is the shadow of the line parallel to the y-axis, as if you were holding a light, a flashlight over here, shining it that way. And the argument's very similar. Anyway, I'm going to let you guys complete the argument, and then likewise for the third one. Okay, neat facts. Okay, so that was lines and planes. We've got 12 minutes, and I'm going to definitely, I feel real confident that we can finish this section on coordinate systems. It's a really short section. Because y'all, let's see how to say this. There's just not that much to say. There's a couple of things to say, but there's some details to be checked, and I'm going to leave those details for y'all. But really, coordinate systems is just an observation about how you can describe points in different ways. Here's what we call the rectangular coordinate system. You have a point. Now, this is what we talked about on. It's like the very first thing we talked about on Wednesday. Right? If you have a point, then you make this box. You look at these corresponding coordinates, x, y, and z, and those are what we call the rectangular coordinates of the point. So that's 3 numbers that tells you a location in 3-dimensional space. Well, it turns out this is not the only way to do that. It turns out there are other ways to use numbers to describe locations. And we're just going to talk about some of those other ones. Here's the first one. Given this point here, instead of looking at the x and y coordinates, I could instead look at what is the angle? What is the angle between the positive part of the x-axis and a direction, in which I can get to the point in question, and then how far do you go in that direction? And you give me a theta and an r, defined like this. You give me a theta and an r, that very clearly gives you a p. It tells you where you are. Okay. So this is called polar coordinates. It's not that big a deal, really, if you think about it. It's just a different way of defining locations. Now, there's a couple little things to worry about here. We are, despite what I've written here, this was awkward. R does not have to be a distance necessarily. I wrote distance here, but it doesn't have to be. We're going to allow R to be negative. So, in other words, given this direction, we're going to allow talking about negative R. So, a positive R would be like that, a negative R would be like that. I don't think that's particularly surprising. It doesn't change the equations any. Another thing to be observed, polar coordinates are not unique. It is unhappy in a way, but instead of using that as my theta, notice I could instead say, turn a full turn plus another pi over 3, and that would still have you going in the correct direction. And that would still, when you give me the distance r, that would still get you to the exact same point. Right? So you can't do that with rectangular coordinates. You can't say, well, for this point, for this value of x, we have that value of y, but you could just as well use a value of x over here. No, you can't, right? The x and y, the rectangular coordinates of a point are unique. And the polar coordinates of a point are not unique. So, that's unfortunate. But anyway, it's just a fact to, get accustomed to. It's not that big a deal. By the way, here's another way to do it. You could take this angle, defining that direction, and in that direction, you go negative distance. That would still get you to the same point. Right? So there's a lot of sort of different polar coordinates for a point. Okay. Here's a little notational thing that I kind of made this up. You're probably not going to see this anywhere else, but I think this is a handy notation to have. Sometimes it's hard to interpret. Well, actually, let me come back up here for a second. It's hard to interpret what you mean when you write down, like, for example, if you were to see someone, they wrote down, 1 comma pi. What is 1 comma pi? Well, 1 comma pi, maybe you're saying that x and y are 1 and pi, respectively. Maybe you're describing the rectangular coordinates of your point. But maybe 1 comma pi are telling you the polar coordinates. Maybe you're saying that the angle is pi. Doesn't pi look like an angle? Right? And r is 1. It would seem pretty reasonable to talk about that point in polar coordinates. So when you write 1 comma pi, it's not, by itself entirely clear what do you mean. And so the way that I The way I arbitrate this is with subscripts, and so if you have a point whose rectangular coordinates are x and y, then I indicate that it's rectangular with a subscript of r. Right? So that it's a sort of like, it's like an asterisk, note to the reader. By the way, I meant this is rectangular coordinates. And likewise, if you want to describe the point in polar coordinates, you could say, hey, subscript polar coordinates. Right? So I'm telling you the polar coordinates of this point, and they are r and theta. Okay. All right. Not hard to persuade yourself. By the way, this is a little bit of trig that you guys can work out on your own, of course. We have a triangle here. Furthermore, that's a right triangle, and therefore you can find relationships between x and y and r and theta. And x is r cosine theta, y is r sine theta. It's real easy to do that exercise. And then tan theta is y over x. Not hard to persuade yourself of that one. Please resist the temptation to say that theta is arctan of y over x. That might or might not be true. Right? Because arctan is only defined as certain values. Arctan is, there's just a certain values that arctan can equal. If arctan is not equal to a whole bunch of different values, that's not how functions work. Right? So arctan means just certain values of theta, but theta need not actually be constrained like that. So I don't know that theta is necessarily arctan of y over x. It might not be. And shame on me for being a little sloppy in exactly that sense here. R might not necessarily be square root of x squared plus y squared. I do know that r squared is x squared plus y squared. That much is clear. But r could be negative. Right? And square root, that symbol means positive. So, sorry about that. I'm going to get that fixed in the next edition of the book. Everybody see what I'm talking about here? So be careful with that. Okay. Cylindrical coordinates. Very often known as the polar coordinates of R3. And I think that's a fine way to describe it. If you have a point, you have a point in 3 space, you can look at its projection down into the xy plane. That projection, you can talk about theta, you can talk about r, and in terms of height, you can just talk about what is the z coordinates, the same z from rectangular coordinates. So let's call it cylindrical coordinates. We'll talk about y later on, but it's called cylindrical coordinates. And you can see why they call it polar coordinates in R3, because, oh my gosh, it's polar coordinates for the x's and the y's. And then with z for the third coordinate. So very, very analogous. But not much has to be said about it in this context. It's polar coordinates in R3. Okay. Now, what you do have to be careful of is spherical coordinates. Also commonly referred to as polar coordinates in R3. That's a mistake. This is really pretty different from polar coordinates. The spherical coordinates of a point involve 2 different angles. We take the point in question, we drop a perpendicular, we look at this plane, that includes the z-axis and the point, right? And that allows us to define 2 angles. There's the theta angle, admittedly, just like polar coordinates, but then there's this other, very importantly different angle. This is the angle measured off of the positive part of the z-axis. It's an angle down like this. So 0 is straight up. So measured down as you sort of rotate down to get to the direction of the point inside of that blue plane. By the way, just for your reference, this symbol that we're using to represent that is it's pronounced phi. P-H-I. It's another Greek letter. So we have the angle theta, we have the angle phi, and then notice that the distance this is very importantly not r, that distance, because r is this. R is down here. And that's not what we're talking about. The distance in question is now the distance from the origin directly to the point in question. It's an angled distance dictated by theta and phi. Right, so it's a very different thing from r. Don't conflate it with r. It's not the same.
Do you still use r in this spherical?
If you were to use r in place of rho, that would be just absolutely wrong.
Okay.
Yeah, it's because it's not the same, right? I mean, r is this very different thing down here, and there you can see they're just not the same thing. Yeah, that's right. And that gives me one last thing I'll mention real quick before I let you go, and that is this symbol. That's another Greek letter. It's the Greek letter rho. Please don't write it as P. It's not a P. It only takes you a few minutes to practice making this little symbol, right? It's a new symbol. Just give yourself a little practice. Please don't. It's not the same as P. So take a few minutes. At the new symbol, right? Take a few minutes and just practice making that little funny-looking little symbol. It's rho, and it's kind of a problem if you write P because, well, P suggests a point. Right? See, I use P there for that point. You can't use P for two different things. Okay, all right. We'll say more about spherical coordinates next time, and I might go ahead. Well, let me look at the exercises and see. I may or may not define the coordinate systems stuff to be due on Tuesday, but I'll send out an email about that pretty soon. Okay, have a great weekend, y'all.